And so we were talking how you could do a queue. When a queue means that is you find new nodes, you put it at the end of the queue, and you handle the node that's been has been found the longest ago, right? And that gives us which? Anybody know which algorithm that gives you? That one's going to be breadth first search. If you use a stack, which is you handle the most recent one, right? That means you keep going down and down and down. So that's going to be depth first search. And if you do some sort of priority queue in which you approximate how far you think each node is from S, and then and you do the one that looks closest, then you get Dijkstra's algorithm. So we're going to look at the queue first. So usually what you do is, we have a we say what the problem is. You have your precondition and postcondition, and from that we figure out what the algorithm is. But today we go all the way to the end, and we skip everything else in between. I pushed the end button, I think.
It's a sign.
It's a sign that we should all go home. Oh, there it is. So today it's kind of funny that it's the reverse, right? We have the algorithm. We're going to be using this queue, and we want to figure out, well, what this algorithm does it do for us? Right, so let's do an example here. We start from S. So we start off with S has been found because we're starting from S, but it hasn't been handled. So what the first thing we do is we take out S and we handle it. And handling it is we find A, B, its neighbors. Right? We put them on the queue in some order. And then A is at the top of the queue. So we take it off the queue and handle it. And we put C and F on the queue, right? And then we take D off and handle its neighbors, and we kind of go like this, right? Everybody kind of, partly I'm feeling we're, people, should we go through slower through this? Everybody got it? All right, so the question is, what order are the nodes found? Right? People get a sort of a pattern of what order they're found. Right? We first find S, then we find its neighbors, and we go through its neighbors. And then we find their neighbors, and we find their neighbors. Right? It's kind of, it's breadth first search. So in some ways, this next guy, the order, so our new sort of or loop invariant kind of, is that the nodes are found, we want to say what's true. We're at the middle of the algorithm. What's true so far? What's true so far is we're finding the neighbors in the order of their distance, the number of edges from S. Right? So the graph might not be a tree. There might be edges everywhere. But you find S, and then you find its neighbors, and then you find their neighbors. Right? And then you find their neighbors. And what's going to be on the queue is, if this is in the front of the queue, then these guys are still in the queue so far, and we take him off the queue and we find their neighbors. So these go on the queue, and we take him off and we find their neighbors. So you might notice I'm a little hyper and going fast. So if you have any questions, you better ask them. All right, so here, let's go again. The S is the only one that's zero distance from S, right? So we first find it. And when we handle it, we put everybody who's distance 1 from S. Right, so now we've got everybody distance 1. And then we go through these guys. And as we go through these guys, as we handle the guys who are distance 1 from S, who gets pushed onto the queue is everybody who's distance 2 from S. Right? Does that make sense? And so now we have everybody distance 2 from S, and then we start working on people who are distance 3 from S. Right? And then you work on the people who are distance 4 from S. And then you're going to go distance 5 from S, but there aren't any, so we're done. Everybody? And so our post condition is then say that, in fact, what we're going to do is we're going to find the shortest path in terms, if the length of the path is defined as the number of edges, we find the shortest path from S to each node. So now, in the end, we have to prove that, that we meet this post condition, right? That we have to prove that for every node, we find a shortest path from S to that node. Right? So there's 2 steps in proving that we've found the shortest path. All right? The first step is that for every node, we have to prove that there is a path of that length. Right? And we also have to prove that there's no shorter path. All right? So how do we prove the first thing? We've gone through the algorithm, and we found this node here. How do we prove that there's a path of this length to this node?
Because if there was a shorter path, you would have found it right.
You're coming down here. That was brilliant for this one. You did the hard one. So the hard one is, how do you know that there's not a shorter path? And the reason is because if there was a shorter path to it, then we would have found it earlier. Right? But how do you know there is a path of this length?
Because you just met neighbors?
Because you just walked it. Right? You traverse this path. That's how you know there's one of that length. All right? So that is because we've found this path. And often in theory we use the idea of witness. There's a path which witnesses the fact that there's a path of that length. And so here, when we're building the path, we know that there's a path of length b to this guy. And when we look at the next edge, then we know there's a path of length b plus 1 to that one. So you keep track of the lengths. And how do we know there's no shorter one? And that's what you said is there's no shorter path because so far we've found the path in order of length, and if there was a shorter length, we would have found it earlier. So that's how we kind of maintaining the loop invariant. You also need a data structure which keeps, for every node, you want to store the shortest path from S to that node. And you don't want to store a separate path for every node because that would take up too much space. And so what we store instead is for every node, you store kind of the parent, the previous node in the, right? So here, if this is node V, then pi of V would come up here, and pi of this node would be this, and pi of this node would be this. And so if you want to know the path from S to V, you follow the pi's backwards, back up to S. That kind of makes sense? Have you seen this before? So when we're doing this trick, right, what would pi of V be? It would be U. Right? And that traverses, that's... So the code is exactly the same as it was before, meaning that we start off with found not handled being S, and nobody's been found yet, and found not handled is going to be a Q, and so you grab the next node that's in the front of the queue, and you handle it. And when you're handling it, you find the neighbors U, and D of V becomes 1 more than D of U, and the parent of V becomes U. All right, so we're going to skip stacks for a minute and go on to priority queues. All right, that's just shortest path. So the problem is you're given a graph, and that graph might be directed or undirected, and every edge has a weight. And our goal, and then a path, the length of the path is the sum of the path edge weights, right? And our goal is we're given a graph, and we're given a node S. And what's key here is we need all the weights to be positive, right? You could have zero, they could have weight 0 or infinity, but they can't have weight negative, because otherwise this algorithm doesn't work. There are other algorithms that work, dynamic programming sort of algorithms, and we probably won't get to them. All right, and our goal is for every node to find the length of the shortest path to that node. All right, so here's an example. If we're starting from S, then we're going to be finding, right, so I guess here's the question. What is the, you can think, what's the shortest path from S to U? Right, it's 4 coming around. Right, but when we're starting at S, what nodes are you going to find first? Right, you're going to find U, and you're going to find W. And then after we find those, where should we search for next? You want to come this way, or no? We want to be walking around here, right? So, is it true that the nodes have been found in the order of their distance from S? Is that true? Well, which node do we find first? We find U first, so this is not true. Right? It's not true that we found the nodes in the order. Right? But what might be true? What order which node should we, now we got here, which node should we handle first? We found these two nodes. Which node should we handle next? We should handle W, and it's the shortest. Right? And it's the closest to S. So we could say we're going to handle in this order. So we're going to handle the order in their distance from S. Right, everybody kind of follow that? That's what our loop invariant is going to say. We want to maintain this loop invariant that says, well, we've been going along and finding nodes, and the order in which we've handled so far is going to be their distance from S. So that's what I've said. And so from that postcondition, from that, yeah?
Can you go back a slide? Say from R to V, the distance was 200, and the distance from
where?
R to V.
R to V is 200?
Then what would the order be? How would it?
Well, you would handle this guy and handle this guy, and then this guy would be too far. Yeah. So then you'd handle him, okay, which would then find this distance too.
Okay.
All right. So again, we want our postcondition. Given that we're maintaining this loop invariant. Oh, did everybody get my comment on the forum? You gotta learn loop invariants, right? Don't, somebody said, oh, well, I won't study the assignment, the test solutions until the exam. But we use loop invariants all through this course, all right? And same with recursion. All right, so we're maintaining this loop invariant up there, and then after we're done, we want to say we found the shortest path. And how do we know we're claiming that the shortest path from S to some node is of length 1,000,000? How do we know that that's the shortest path? Well, first, we want to say there is a path of length 1,000,000. Why? Because we traced it out. How do we know that there's not a shorter path? And again, there's not a shorter path because otherwise, by the loop invariant, we would have found it earlier. Or handled it earlier, right? Because we're handling it in that order. All right, so the basic steps, as we've seen, is, right, we don't, it kind of sounds like a circular argument because we don't know the distances, the shortest path from S to various nodes. But, we're going to keep a sense of what is the shortest path, length of the shortest path that we know about. Right? I think we call them the shortest handled path. And so for each node, we'll keep a sense of how far it is from S. Right? So we keep an approximate distance, which will be of all the paths that we know about, we've handled, it'll be the shortest one. And so dv will give you the length of the shortest path that we've seen so far. And the one we handle next will be the one that has the smallest d value. All right, so we're maintaining this d value, which tells us that the shortest path we've seen so far is of this length. And we'll keep updating the d values as we go along. So here, for example, suppose if the shortest path, we know the shortest handled path up to v has this length, and the shortest handled path up to u is of this length, right? And then suddenly we handle this new edge. We now have this new edge that we know about. We didn't know about this edge before. So what do we have to update now? Right? We have a new path here to consider that we've never considered before. Right? And the length of this path is du plus the weight of this edge. Right? So the shortest path that we've now considered could have been our previous path of length dv, right? Or it could be this new path of this length. So we update dv to being the minimum of these two. Is that right? And if there's a tie, then, I don't know, you flip a coin. It doesn't matter which one you take. So the code is pretty straightforward. It's the same as we did before. We have the not handled, the guys who have been found and not handled is a priority queue, meaning each node has a value d, and what data structure do we use for priority queues? Heaps, right? It's in a heap. They're organized in a heap, and we grab the node u that has the smallest d value, right? And we handle u. And how do we handle u? Is we find every node v connected to it. And then we update dv to being right, the new found length, the length of the new path, which goes from s to u to v, is of length, just as we said, right? The length to u plus that edge. And right, and if the new path is shorter than the old path, then we update the d to being the length of the new path, and we change who v's parent is. Right, now the path from s to v will go through u. Does that make sense? So we're going to do a little bit more formal proofs about this. We need a definition of really what do we mean formally about a handled path. All right, well, you know, our algorithm is handling nodes, right? So suppose that these are our handled nodes. And what does it mean to be a handled node? It means that you've kind of handled all the edges out of them. Right? So these edges out of the handled nodes are all handled edges. Right? And the d value, right? So those are the handled edges. And the handled paths, right? This is a handled path to here. And this is a handled path. But this is another path to this node. But it's not handled because we haven't looked at these edges yet. Right? Does that make sense? So the d value for this will be the shortest path of all the paths that start at s, go through handled nodes, and then take one last edge to the node. Right? Those are the kind of paths that we know about, and the d value of this node will be the best path of those.
I'm lost.
All right, good.
The ones
Everybody else probably is too.
The ones with the orange border, are those the ones that are handled?
No. The guys in the circle are handled.
So how did you handle this? second.
That's a good question, and people ask me that question often. But this is just this. There are a lot of edges here that don't have in the picture,
okay.
right? So there are other edges in here. Maybe I should change the picture because a lot of people talk about that. But this is just an example of how you can have very complex paths that we haven't considered yet. Do people kind of follow what we're saying here? Right, there are a lot of edges in here, and they go a lot of edges that are handled in here, and the other handled edges are from the handled nodes out, have been handled. But these guys we haven't handled, and the paths that we're considering, the paths we call handled, are the paths that start at S, go through handled nodes however you want, and then one last edge to a node here. And then the D value for this will be the shortest of those.
So why is the one being found, but it's not handled? So it's found, but it's not handled, right?
Right. So we found this node.
The one that's like
This
in
one
the
here?
circle, the one that's in the circle.
Yeah, this one, yeah.
Yeah.
It's found, but it's not.
And also handle it.
It's handled.
Oh.
Put an extra edge in here to it.
Oh, okay.
Shouldn't that black
What's
be
that
red?
black?
Yeah. Why is it?
Black. Is there a line there or when is it?
I think the black survives from when we said those are the handled edges, right? And then which paths? What are the paths to this node that are handled, right? It's just paths that look like this. Paths that look like this to here, right? Those are the handled paths, and these other weird paths are not handled.
The black line should be red. Because if there is an edge, in order to have handled that node, there must be an edge to it from S, and therefore that path is handled.
Yeah, so there would be a path to this, but this is just a subset. What are the handled paths to this node?
Yeah.
Right? So I could change these picture here. I'll remember that. Change this picture. All right, so our loop invariant, it says that for every node, the dv is the length of the shortest handled path to that node. But moreover, that for the nodes that have been handled already, then we have the absolute shortest path. All right? So this is what our loop invariant says, is that we've handled some nodes, right? And the nodes that we've handled, we have the shortest path to them, the absolute shortest path. And for the other nodes that haven't been handled, we have the shortest handled path, right? The shortest path that starts here, goes some distance, and then one last edge. And nodes that haven't been found already, you've never found them, we don't really worry about them so much. What's their d value going to be?